I am Aarya. I am a class 8 student from Samashti International School. Today I will be talking about the standard model and how our universe works. So, if we look at our universe, it is a very vast place. But not very long ago, the entire universe was all at a point before the Big Bang. Actually, this is the best way to observe the universe at a very small scale. That way we can understand what is happening to it. So if we zoom into the universe, we see that there are galaxies. If we zoom into the galaxies, that's the Earth. If we zoom into the Earth, we have humans. Zoom into humans, you have cells. Zoom into cells, you have atoms. Zoom into atoms, and you have the subatomic particles. Subatomic particles are normally broken down into the hadrons and the leptons, and the hadrons are the protons and the neutrons. So if you break the hadrons down, you get the quarks. So this is eventually broken down into the elementary particles, which is the standard model. The standard model, so I'm going to be talking about that now. And as Einstein once said, the laws of mathematics are certain about what is not real, but it is not certain about what is real. So this is a very inspiring quote, and let's move on and learn about the standard model now. So standard model, if we see, it can be divided into the fermions and the bosons. So the fermions consist of the quarks and leptons, and the bosons have many types of bosons in themselves. So I will first talk only about the fermions, and then I'll move on to the bosons. So now I'm talking about the fermions, specifically the quarks. Next slide, please. So in the quarks, we have three generations of quarks, and these quarks make up the hadrons, which I was talking about, such as the proton and the neutrons, and they are classified into generations based on their mass. So the up and down have a mass of 2.4 mega electron volts and an approximate mass of 4.8 mega electron volts, and they both have a spin of half, and the charge of the up is 2/3 and the charge of the down is -1/3. Now if we look at the second generation particles, the charm and the stranges. So the strange has a mass of 1.27 giga electron volts, and the strange has a mass of 1.104 mega electron volts. So, and it has a charge of -3, and the charm has a strange of 2/3, and both of them have a spin of half. So, and if we look at the third one, at the top and the bottom, which is the third generation, then they both also have spin of 1/2, and the charge of the bottom is also 1/3, and the charge of the top is also 1/3. So in summary, we can say that the mass of the bottom particles is generally less, except for the first generation, and the charges of the top particles are the same, and the charges of the bottom particles are the same, and they all have spin of 1/2. They all have antimatter counterparts as well, such as the anti-up, anti-down, anti-charm, anti-strange, anti-top, and anti-bottom. They have the opposite stranges, like -2/3 and 1/3, -2/3, 1/3, etc. Now I'll be talking about the leptons. So in an atom, the leptons, so the quarks make up the nucleus of the atom, and leptons revolve around that. So like we see the electron, so the electron revolves around the atom. So that will be coming under the leptons. So leptons will be revolving around the atom, not limited to revolving around the atom, but that's a good example of them. So over here, so they are a group of subatomic particles. So the quarks, they make up bigger particles, such as hadrons, based on the strong force. So they use the strong force to interact and exchange messages and all, and they make up protons and neutrons. These, on the other hand, do not use the strong force. They use the weak force to interact with, use the weak and gravitational force to interact with other particles, such as the hadron, and they use the electromagnetic force to interact with each other, and that includes the study of electronics. So the electrons, they communicate with each other on the electromagnetic force. So everything has so we have three particles: the electron, the muon, and the tau. torn, which are the free generations, and they all have neutrino counterparts. So neutrino counterparts also have a spin of 1/2. They have very less masses, and they have all of their masses are less than 15 mega electron volts, so it's not very high. And then they have zero charge. All of the leptons have -1 charge, and the electron, the muon, and the proton, all these have different masses. So the electron has a mass of 0.5 mega electron volts, the muon has a mass of 1.6 mega electron volts, and the proton has a mass of 1.7 giga electron volts. So they all also have antimatter counterparts. So the positron for the electron, and such as that, like we have the positron and the positron neutrino, etc. So names are a little more complex, but it just has 1 charge and 0 charge for that one. Same. So yeah. Now let's talk about the bosons. So the bosons actually govern the fundamental forces. So the fundamental forces in the universe are governed by these bosons. We have several types of bosons, the gauge and the scalar ones. I'll be coming to that. Over here, as you can see, these are the 4 fundamental forces embodied as particles. But they are not exactly the fundamental forces. They are like a remote to a TV. Let's imagine you have a TV, and these are the remote to the TV. So they enable the TV to work, but they are not the TV. So TV is the fundamental forces, and these are the particles that govern them. So we have a graviton, which is responsible for the gravitational force. That is not yet discovered, so I will not be talking about that. But that is a proposed part of the standard model, but it's not yet confirmed to be discovered, so I'm not going to be talking much about that. The photon is responsible for the electromagnetic force. It has a spin of 1, mass of approximately 0. It's close to 0, it's not exactly 0, and a charge of 0. And then we have the W and Z bosons with masses of 80.4 and 91 respectively, and then a charge of -1 for the W minus and charge of +1 for the W plus boson. And they all have spin of 1. And then we have the Z boson, which has a charge of 0 and it has a mass of 91 giga electron volts. And then we have the gluon. So these are the weak electron force. So this is the weak nuclear force, and they are responsible for the interactions between the leptons and the hadrons. This makes the hadron. This holds the quarks together. It's known as the gluon. Its mass is not yet very determined, and charge also is 0. It has spin of 1. As I was saying before, so in the bosons, we have 2 types of bosons, the gauge bosons and the scalar bosons. So in the gauge bosons, so the gauge bosons are what I have explained about in the previous slide, and they are the forces that govern the interactions of the particles. So these are the primary fundamental force particles, and those are the scalar bosons. So the scalar has only a magnitude; it does not have a direction. And in this context, a scalar means a constant, so they have a spin of 0. That's why they are known as scalar bosons. And they can be used to scale up and down the forces, and they have many uses in the quantum, as discussed in the quantum field theory. And they have a spin of 0, which is the only boson to have a spin of 0, which is a very special characteristic of these. Most of the gauge bosons do not have a spin of 0, the discovered ones, that is. Now I would like to summarize in a very basic way. So we can think of the subatomic particles as a house. So we'll have the universe as a house, and the bosons are the cement, so because they stick around, and the fermions, which are the quarks and the leptons, they are the bricks. So the cement holds the bricks together. And then we can think of the bosons and the fermions only as a set of building blocks. So let's take the kids' building blocks. The kids make around like Legos. So they can build upon it, and they are all of they may or may not be of all equal lengths and equal strengths. And the bosons are like remotes to the fundamental forces. Thank you very much. I am Aarya Tiwari.